One of the most baffling dark openings and the universe's bizarre phenomena remain the focus of intense examination and interest among space experts, physicists, and other scientists alike. Referred to as their monstrous total weight and gravitational pull, the absence of visible light from them addresses a limit beyond which the established rules of physical science stop applying. First speculated by Albert Einstein in 1916 as a consequence of his general theory of relativity, dark openings were simply speculative until mechanical advancements allowed their indirect identification during the 20th century. The turning point came during the 1960s when experts in space research, the Cygnus group of stars, accidentally discovered a brilliant star, an unusual celestial object, a blue star that emits X-rays with high energy. This star, circling an unnoticed companion, challenged regular explanations until it was revealed to be caught in a hug of gravitation with a massive dark opening, Cygnus X1. The clear discovery of Cygnus X1 proved the existence of dark openings and began a new era of investigation into these infinite conundrums. Found around 6,000 light-years from Earth, Cygnus X1 has amazing characteristics, extremely dense and uses a force of gravity so strong that not even light can escape it. This defining characteristic gave it its name, dark opening. It captures the essence of these mysterious objects. Subsequent exploration efforts have uncovered a variety of dark openings scattered throughout the universe. Estimates suggest that the Milky Way galaxy alone may harbor more than 100 million dark openings. Despite their elusive nature, which makes precise detection challenging, space experts have identified several candidates within our galaxy. These range from stellar dark openings, made by the remains of massive stars, to extremely large dark openings residing at the centers of galaxies. The gravitational impact of the dark openings goes well beyond their immediate vicinity, influencing the components of cosmic development and the fate of surrounding matter. Objects that get too close to a pitch-black opening confront a destiny set by its relentless force. They are drawn unyieldingly toward the final turning point, on the event horizon, where they are subjected to extreme tides and, in the end, consumed by the singularity at the dark opening's core. This catastrophic interaction, referred to as spaghettification, represents the extreme appearance of a dark opening's gravitational strength. As an object closes in on the event horizon, the gravitational gradient across its length becomes so extreme that it is stretched and twisted into a filamentary structure resembling strands of spaghetti. The effects of the dark opening's forces can break through the internal ties maintaining the object's integrity, resulting in its disintegration into a stream of matter destined to merge with the core. Despite the enticement of dark openings as invaluable laboratories for testing the limits of physical theory, they remain shrouded in mystery and intrigue. The mission to unravel their secrecy doesn't stop, driven by a desire to comprehend fundamental properties of space, time, and gravity itself. In the vastness of space, dark openings remain silent sentinels, urging humanity to investigate the depths of the unknown and expand the limits of human understanding. Despite the considerable distance separating us from the nearest dark opening, roughly 1,500 light-years away, questions and concerns about their potential impact persist. In 2019, researchers achieved a historic breakthrough by capturing the first clear image of a dark opening, specifically M87, which lies in the middle of the M87 galaxy. This remarkable achievement provided crucial insights into the nature of dark openings and their elusive structure. The visual data revealed that dark openings have intricate layers, challenging the traditional perception of them as solitary entities of pure nothingness. Through meticulous analysis and image stitching, researchers identified 3 distinct layers within a dark opening. At the outermost layer lies the event horizon, a critical boundary marking the point of no return. Once an object exceeds this limit, gravitational forces become insurmountable, ensuring its inevitable plunge into the dark opening's depths. Moving inward, the second layer is made up of the photon sphere, where light orbits the dark opening in perpetual bondage. Any photons that dare to venture into this realm succumb to the overwhelming gravitational pull, trapped forever within the dark's cosmic embrace. At the very center of the gloom lies the singularity, the third and final layer, where the laws of physics reach their ultimate limits. Matter undergoes unfathomable compression, crashing down to a point of infinite density. It is within this enigmatic singularity that the conventional laws governing the universe cease to apply, plunging researchers into a realm of profound uncertainty and theoretical speculation. The complexity of dark openings and their inherent variability present significant challenges to our understanding. While they adhere to a common 3-layer structure, each dark opening has particular characteristics and behaviors, defying simple categorization. As such, traditional methods of scientific inquiry prove insufficient for studying these cosmic behemoths, necessitating innovative approaches to unravel their mysteries. The primary method of observation is still indirect, as direct investigation is rendered unfeasible by the immense barriers posed by their gravitational forces. Attempts to insert probes into dark openings would inevitably result in their destruction, crushed into obscurity by the unstoppable forces at work. Nevertheless, researchers persist in their quest to learn the mysteries of these cosmic giants. Numerous theories about their behavior and origins, from stellar collapse to cosmic dynamics, offer tantalizing glimpses into their nature. Particularly, NASA's investigation of M87's cosmic center revealed convincing proof of a supermassive dark opening, exerting its gravitational pull on a vast cosmos. Despite these mysteries, the pursuit of knowledge continues, motivated by the inherent curiosity of humanity and a desire to comprehend the incomprehensible. While dark openings may be an unsolvable mystery, the steadfast dedication of scientific inquiry promises to illuminate even the gloomiest areas of the universe, unraveling the profound secrets hidden within. Roy Kerr's groundbreaking work in 1963 presented a paradigm-shifting perspective on dark openings, proposing a revolutionary theory of rotating black holes that defied conventional understanding. Kerr's model was based on the idea of the ergosphere, a region surrounding the dark opening where divergent forces balance collapse by gravitation, preventing matter from collapsing further. This innovative domain displayed curious deviations from traditional physics, hinting at the profound mysteries concealed within dark openings. However, the most intriguing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure represents a potential gateway through spacetime, facilitating communication between distant regions of the universe or even parallel universes. The idea of wormholes stems from the intricate interplay between Einstein's theory of general relativity and the fabric of existence. In this framework, reality is woven into a four-dimensional structure. The quest for a unified theory that reconciles gravity and quantum mechanics has spurred the search for a comprehensive system that can explain all fundamental interactions in the universe. This so-called theory of everything aims to bridge the gap between general relativity, which governs massive celestial bodies like stars and galaxies, and quantum mechanics, which rules the subatomic world. Dark openings, or black holes, serve as the ultimate testing grounds for such a theory. At their cores, where immense mass is compressed into an infinitely small point, both gravitational and quantum effects become dominant. However, current models fail to cohesively describe this extreme environment. The singularity, as predicted by relativity, is a place of infinite density and zero volume, an idea that quantum theory struggles to accept without yielding nonsensical results. To overcome this paradox, physicists have proposed numerous candidates for a unified framework, including string theory and loop quantum gravity. String theory posits that all fundamental particles are not point-like dots but rather tiny vibrating strings whose different vibration modes give rise to various particle properties. This elegant concept allows gravity to be described within the same theoretical framework as other forces, offering a potential solution to the incompatibility between relativity and quantum mechanics. Loop quantum gravity, on the other hand, attempts to quantize spacetime itself, suggesting that space is not continuous but made up of discrete loops or chunks. According to this theory, the singularity inside a black hole may not exist as traditionally imagined. Instead, it could be replaced by a dense quantum region where the gravitational field is repelled, possibly leading to a bounce or a new universe on the other side, a speculative but fascinating idea. While these theories remain largely unproven, the ongoing observation of dark openings continues to offer valuable data. Instruments such as the Event Horizon Telescope, EHT, LIGO, and Virgo are pushing the boundaries of our knowledge. The detection of gravitational waves, ripples in spacetime caused by massive cosmic events like black hole mergers, has opened an entirely new window into the universe. These waves carry information about cataclysmic processes that were once invisible to traditional telescopes. In 2015, the first direct detection of gravitational waves confirmed a key prediction of Einstein's general theory of relativity and provided direct evidence of merging black holes. Since then, dozens of such events have been recorded, offering clues about the formation, distribution, and behavior of these dark giants. Despite all these discoveries, many questions remain. What exactly happens at the singularity? Can anything ever escape a black hole's grasp? Are wormholes real and, if so, could they be stable enough to traverse? Could black holes be gateways to other dimensions or universes? These questions highlight the awe-inspiring complexity of black holes. They are not just destructive cosmic monsters, they are also fertile grounds for discovery and wonder. As our tools become more sophisticated and our theories more refined, we inch closer to deciphering the mysteries locked within them. In the end, black holes challenge not just our scientific understanding but our philosophical perspective as well. They ask us to confront the limits of knowledge, the nature of time and space, and our place in a vast and mysterious universe. Bringing together all of the fundamental forces and particles in the universe, at the forefront of this endeavor stands Michio Kaku, a well-known theoretical physicist whose groundbreaking work has propelled the study of superstring theory. Superstring theory represents a dramatic deviation from standard ideal models, hypothesizing that fundamental particles are not point-like entities but instead microscopic vibrating strings. These strings, similar to those of a musical instrument, resonate at specific frequencies, giving rise to the various forces and particles found in nature. In this paradigm, the universe becomes like a grand symphony, each particle corresponding to a unique harmonic resonance. One of the most striking implications of superstring theory is its potential to explain enigmatic phenomena associated with dark matter, wormholes, and other exotic solutions to Einstein's equations of gravity. As the fabric of spacetime is twisted by the dynamic motion of strings, it results in the development of gravitational singularities and topological anomalies. However, the elegance of superstring theory masks its inherent complexity, as it necessitates the existence of supplementary dimensions. Besides the three familiar spatial dimensions and one temporal dimension, these extra dimensions, hidden from direct observation, pose a significant challenge to human intuition. Models such as the analogy of fish living in a lake with only two dimensions provide a glimpse into the elusive nature of these higher dimensional realms. The compactification of these extra dimensions, akin to the folding of a rolled-up piece of paper, renders them imperceptible at everyday scales. Yet, their influence permeates the very fabric of reality. While the precise nature of these hidden dimensions remains elusive, their theoretical presence offers a promising explanation for the complex structures and anomalies observed in the universe. Additionally, the mathematical underpinnings of superstring theory have sparked a renaissance in mathematical physics, revealing deep connections between dynamic mathematical patterns and physical phenomena. Indeed, the search for a complete theory has catalyzed the union of disciplines, shedding light on the profound interplay between the natural and mathematical sciences. Despite its elegance and scientific potential, superstring theory remains an untested framework, awaiting experimental validation. The elusiveness of additional dimensions constitutes a formidable obstacle to experimental verification, relegating superstring theory to the realm of mathematical speculation. Nevertheless, the bold concept of superstring theory continues to captivate the minds of researchers and enthusiasts alike, enticing the human race to embark on a journey of intellectual discovery and exploration. As we progress further into the unknown domains of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the vast mysteries of the universe, poised on the threshold of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum dark openings has long perplexed physicists, representing a monumental challenge to our understanding of the fundamental nature of the universe. Despite numerous efforts, the elusive solution has remained beyond our grasp. Edward Witten, at the Institute for Advanced Study at Princeton, described superstring theory as the physics of the 21st century that accidentally fell into the 20th century. However, recent advancements have injected new hope into the quest for understanding quantum dark openings. Several groups of physicists have independently reported a significant breakthrough, revealing that string theory could provide a complete solution to the issue, though within the more constrained context of two dimensions, rather than the full 10-dimensional framework set forth by conventional superstring theory. While this is an encouraging development, the search for an all-encompassing solution remains ongoing. The complexities of the situation present significant obstacles. The search for a unified theory of everything beckons us to probe the deepest recesses of cosmic existence, where the boundaries between reality and theory become hazy, and the secrets of the universe await discovery. The study of dark spaces carries significant implications for our understanding of the universe, challenging our notions of reality and raising questions about the very nature of existence. The interaction between dark openings and other astronomical phenomena, such as neutron stars and gamma bursts, reveals the intricate processes at work. The investigation of dark openings and their interaction with surrounding matter continues to reveal a wealth of intriguing phenomena. One of the most fascinating aspects of these cosmic giants is their ability to warp spacetime so intensely that they create gravitational waves, ripples in the fabric of spacetime itself. These waves travel outward from the source, carrying information about the dynamics of events such as the collision or merger of two black holes or a stellar mass black hole with a neutron star. Detecting these waves has become a powerful tool for studying the universe, particularly since the first direct observation of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. This milestone opened a new avenue for research, a new astrophysical window that allows scientists to observe some of the most significant cosmic events, like black hole mergers, with unprecedented clarity. As these observations continue to accumulate, they bring us closer to comprehending the true nature of dark openings, their formation, and their evolution. One particularly puzzling aspect is the behavior of matter as it falls into a black hole. While current models suggest that matter undergoes significant changes as it nears the singularity, questions remain about the fate of information contained within that matter. This is known as the information paradox, a problem that has perplexed physicists for decades. According to quantum mechanics, information about a particle's state cannot be lost, whereas black holes appear to erase all information that falls into them, challenging the foundations of quantum theory. Resolving this paradox remains one of the key objectives in modern theoretical physics. Additionally, the potential connection between dark openings and the broader structure of the universe remains an area of active investigation. Some hypotheses suggest that supermassive black holes at the centers of galaxies play a critical role in shaping individual galaxies, influencing their growth and even driving the formation of stars and planetary systems. The relationship between these cosmic giants and the dark matter and dark energy that dominate the universe is also under intense scrutiny. Understanding how dark openings interact with these enigmatic parts of the cosmos could be essential to unlocking many of the greatest secrets of the universe. This intricate web of interconnections between black holes, dark matter, and dark energy invites a deeper philosophical and scientific reflection. If black holes can indeed influence galaxy formation and cosmic evolution, then understanding their nature might not just illuminate the mechanics of spacetime, but the very architecture of existence itself. Moreover, recent theories propose that black holes may serve as gateways or bridges to other regions of spacetime, so-called wormholes, whose theoretical foundations lie within the equations of general relativity but whose physical existence remains speculative. If these structures do exist and can be stabilized, they could radically alter our understanding of causality, time travel, and interstellar exploration. Yet, these concepts remain largely within the realm of high-level mathematics and theoretical frameworks. To move them into the domain of empirical science, physicists are turning to increasingly sophisticated tools, both terrestrial and space-based. Projects like the James Webb Space Telescope, the Event Horizon Telescope, and next-generation particle accelerators aim to probe the universe with unprecedented clarity, perhaps even providing the indirect evidence needed to support or refute aspects of superstring theory. At the heart of this scientific journey lies a simple but profound question. What is the universe made of, and why does it behave the way it does? While traditional physics has provided a solid foundation for understanding the macroscopic and microscopic worlds, gaps in the theory, especially at the intersection of gravity and quantum mechanics, suggest that we are only scratching the surface. Superstring theory, with its elegant symmetries and mathematical depth, offers a tantalizing possibility that all forces and particles are unified through the vibration of one-dimensional strings in a higher-dimensional space. If validated, it would mark the most significant leap in our understanding of the universe since Einstein's theory of relativity or the formulation of quantum mechanics. But for now, the theory remains incomplete, a masterpiece still in progress. It represents not only a scientific theory but a philosophical and imaginative leap, a reminder that human curiosity knows no bounds. As scientists across the globe continue to decode the cosmic symphony, guided by mathematical rigor and driven by awe, the quest for a unified theory of everything continues. And in that pursuit, we inch closer to the ultimate truth about the cosmos, not just as observers, but as participants in its unfolding story.